6 minutes and 46 seconds on a 20.8-kilometer track. A total rejection of a century-old automotive metallurgy baseline secured this lap time. The Xiaomi SU7 Ultra bypassed the Porsche Taycan Turbo GT on the Nürburgring Nordschleife. This dynamic performance relies heavily on a radically new chassis geometry, rather than just raw electrical motor output. To achieve this high torsional rigidity, engineers discarded standard aluminum variations. An algorithmic synthesis generated an entirely new alloy formula. The software analyzed millions of crystal lattice structures to find the optimal ratio of silicon and magnesium. The manufacturing process shifted from incremental assembly to massive physical force. The production relies on giant high-pressure die casting complexes. A single casting machine occupies a physical footprint equivalent to 2 professional basketball courts. Inside the main injection chamber, the physical environment mimics a specialized industrial furnace. The internal temperature forces the new synthetic alloy into a highly fluid state. Hydraulic rams activate. They push the molten metal into a complex steel mold at high velocity. Intense heat radiates outward, raising the ambient temperature near the heavy machinery. Clamping mechanisms lock the die together under thousands of metric tons of hydraulic pressure. This extreme pressure drives the liquid metal into every microscopic cavity before solidification begins. The press shapes a massive rear chassis section in a single continuous strike. 120 seconds. Casting one complete structural segment requires that exact duration. A manufacturing phase that normally demands hours of precise robotic spot welding now finishes in under 2 minutes. The press opens. The rapidly cooling solid metal retains the exact structural geometry dictated by the software. The fast cycle time eliminates the physical weak points typically found in joined steel panels. There are no overlapping metal seams. There are no microscopic stress concentrations between welded joints. The entire production sequence utilizes functional heavy hardware. Multiple die casting complexes are actively running and producing these segments inside the primary Beijing manufacturing facility today. Why did engineers discard standard welding methods entirely? To integrate the heavy battery module directly into the core structural frame. Integrating a dense power source shatters the conventional assembly logic, where manufacturers stitch a vehicle structure together from hundreds of flat steel sheets. For over 70 years, automotive production relied on a simple sequence of taking cold steel panels, forming them under immense mechanical presses, and joining the fragments. A typical chassis comprises hundreds of individual stamped metal components. Spot welding fuses these fragments together through thousands of localized points scattered across the entire structural skeleton. While the approach functions for lighter internal combustion platforms, the material physics change dramatically under sustained load. Every single weld point represents a microzone of metallurgical stress. During dynamic driving, kinetic energy travels through the rigid steel matrix. The thousands of connection points experience continuous high-frequency vibration, leading to gradual physical material fatigue along the metal seams. The structure flexes. Each fused joint acts as a mechanical bottleneck under torsion. The transition to electric propulsion severely amplified these physical limitations across the industry. A standard electric vehicle battery pack weighs anywhere from 400 to 700 kilograms. When engineers bolt this massive chemical block under a traditional stamped steel floor, the dynamic load profile shifts entirely. The power unit becomes a centralized dead weight, exerting immense shear force on the surrounding thin, welded joints. To prevent structural deformation under this localized stress, manufacturers must reinforce the steel frame, thereby increasing the overall vehicle mass. Moving a heavier reinforced chassis demands a larger energy capacity, which requires an even heavier battery pack, instantly triggering an inescapable upward spiral of escalating vehicle weight. To halt this escalating mass spiral, automotive engineers discarded traditional spot welding techniques. They transitioned to injecting liquid aluminum under intense hydraulic pressure. A standard industrial gigapress clamps the heavy steel mold closed with a mechanical force of 6,000 to 9,000 tons. Molten metal fills the internal structural cavity in milliseconds. Exactly 60 separate stamped steel components vanish from the automated assembly line. One solid piece emerges. This direct high-pressure injection drastically reduces the total vehicle chassis weight, yet this unified physical geometry conceals a microscopic defect deep inside the cooled alloy. That internal structural flaw creates a critical engineering paradox. Molten aluminum solidifies rapidly inside high-pressure molds. This rapid cooling locks microscopic crystals into completely chaotic configurations. The resulting metallic matrix lacks uniform directional strength. It remains dangerously brittle under high dynamic loads. Fixing this internal architecture requires extensive thermal intervention. The massive cast component must enter industrial baking furnaces. Temperatures exceed 500 degrees Celsius for several continuous hours. The prolonged heat agitates random atomic bonds and realigns microscopic crystals into a rigid lattice. This specific metallurgical phase shifts the aluminum from fragile to incredibly durable. Yet this microscopic stabilization causes massive macroscopic failure. The intensive heat treatment forces the unified chassis geometry to warp. The immense aluminum casting physically twists as the internal structure reorganizes over time. Thermal expansion and contraction alter critical structural dimensions by several millimeters. These slight geometric shifts cascade fatally throughout the final vehicle assembly. Suspension mounting points drift out of calculated operational tolerances. Door frames lose their exact alignment with the surrounding exterior body panels. The mandatory thermal cycle permanently destroys the tight dimensional accuracy achieved during the initial injection molding. Automotive manufacturers hit a definitive physical wall right here. They are forced to compromise between exact geometric shape and necessary structural strength. Escaping this high-temperature dependency demands a completely novel material chemistry. Automotive engineers systematically evaluated every single commercially available metal composition. They tested standard aluminum mixtures against extreme structural stress parameters. The global materials market offered exactly 0 alloys capable of absorbing heavy impacts without prior thermal processing. Every conventional option strictly required high-temperature baking to reach the minimum safety threshold. The entire manufacturing sector eventually accepted this severe material limitation as a permanent physical boundary. How can engineers stabilize unified chassis geometry during mandatory heating above 500 degrees? The industry conceded that standard metallurgy offered no workarounds. The fundamental conflict between microscopic crystalline alignment and macroscopic dimensional stability appeared totally unresolvable using traditional methods. To bypass this physical deadlock, engineers deployed a deep learning algorithm to process millions of molecular structures. It searches for a single configuration that eliminates the need for a high-temperature oven. The computational system systematically evaluates interatomic bond energies to predict exactly how different elemental mixtures will crystallize during the rapid cooling phase. This advanced computational approach allows researchers to forecast the precise microscopic alignment and structural integrity of a material without ever conducting physical stress tests. Virtual atoms snap together. The algorithm continuously alters the specific ratios of aluminum, silicon, magnesium, and various heavy rare earth elements, analyzing the thermodynamic stability of each new crystalline lattice. It maps out exactly how the metallic bonds will behave as the internal temperature drops from a molten liquid state down to solid ambient factory conditions. The software monitors the simulated lattice for microscopic fractures or geometric warping during this thermal transition. During this computational phase, the artificial intelligence evaluated 10,160,000 distinct alloy combinations. If a human metallurgical team cast and physically tested one new material formula every single day, achieving this exact volume of experimental data would require over 27,000 years of continuous laboratory work. The deep learning network condensed this immense timeline into a parallel computing operation running across high-performance servers. Millions of iterations fail. The system eventually isolates the exact microscopic configurations that resist structural thermal distortion. The entire development sequence relies purely on iterating through molecular bonds rather than performing physical trial and error on the factory floor. Engineers successfully secured the precise molecular formula for a dimensionally stable aluminum alloy before the very first industrial smelting furnace was ever turned on. That computational output yielded the exact chemical composition for Titan metal. It blocks thermal deformation entirely. The material requires 0 heat treatment cycles after the initial high-pressure casting process. No secondary baking phase occurs. Production accelerates. Bypassing this traditional thermodynamic step prevents the microscopic structural warping that inherently degrades dimensional accuracy in standard automotive manufacturing. The newly cast components cool rapidly while retaining their mathematically precise geometric shapes. Assembly tolerances remain consistently tight. Eliminating these massive industrial ovens systematically reduces overall energy consumption across the entire production line. Now, automated robotic handlers prepare to inject this thermodynamically stable molten metal directly into the primary casting press. This new molecular structure demands immense physical pressure to lock the molten metal inside the die during the injection process. The equipment engineered for this specific task, designated as the Hypercasting machine, covers a physical footprint of approximately 850 square meters. The entire primary installation weighs over 1,000 tons. Inside this heavy casting complex, the custom alloy reaches a sustained temperature of 700 degrees Celsius. The liquid metal does not merely pour into the cavity under its own weight. It is injected directly into the complex steel geometry at velocities reaching between 80 and 100 meters per second. This extreme kinetic energy serves a highly specific purpose in preventing structural porosity. If the filling phase happens too slowly, microscopic air bubbles become permanently trapped inside the rapidly cooling metal matrix. These microscopic voids act as hidden stress concentrations, essentially operating as starting points for internal fractures when the finished chassis experiences heavy torsional loads. The high injection speed ensures the liquid alloy completely fills every section of the die before any atmospheric gas can form those dangerous internal pockets. To prevent the kinetic impact of the injected molten metal from physically blowing the two halves of the mold apart, the system engages its primary hydraulic locks, 9,100 tons of clamping force. Under this massive pressure, metal heated to 700 degrees Celsius fills the cavity, forming the entire rear chassis structure. Traditional automotive manufacturing relies on complex structural fragmentation. A standard rear floor section requires 72 separate stamped steel parts. Assembly demands 840 individual spot welds. Standard robotic welding takes 1 to 2 seconds per point. Connecting those 840 joints consumes tens of minutes. This calculation ignores the time needed for precise alignment and physical clamping. The conventional method introduces hundreds of potential mechanical failure points. The Hypercasting machine bypasses that entire sequential process. 72 isolated components instantly become a single continuous structure. 840 weak weld seams drop to zero. The complete injection, pressure holding, and rapid cooling cycle requires exactly 100 seconds. This physical elimination of mechanical joints fundamentally alters vehicle dynamics. The monolithic cast piece weighs 17% less than a welded steel equivalent. Structural rigidity increases while cabin road noise drops by 2 decibels. There are no overlapping panels or microscopic welding gaps left to vibrate at high speeds. Quality control immediately shifts from basic visual inspection to deep structural analysis. The production protocol removes human subjectivity. High-precision laser arrays rapidly map the complex dimensional accuracy. Finally, an automated X-ray scanner analyzes the internal density of the solid alloy before the heavy press extracts the finished part. Eliminating 840 manual welds and forging a monolithic rear structure directly open the pathway for a completely restructured power architecture. Traditional engineering treats the energy source as passive cargo. Standard electric vehicle battery packs frequently reach thicknesses between 150 and 200 millimeters. These conventional units simply bolt beneath the floor pan. They add 400 to 600 kilograms of isolated ballast mass that contributes nothing to structural integrity. The engineers recognized that integrating this dead weight into the primary load-bearing skeleton required a radical geometric manipulation. This integration utilizes cell-to-body architecture to alter how mechanical stress moves through the lower chassis. Instead of isolating the chemical storage inside a separate vault, the upper boundary of the battery array forms the physical cabin floor. The power cells absorb kinetic forces directly. This transforms the energy module into a rigid structural crossmember. Making the battery a skeletal component demanded a strict layout adjustment to guarantee safety without expanding vertical dimensions. The engineering team executed a complete spatial inversion, rotating every single battery cell exactly 180 degrees from standard orientation. This specific 180-degree rotation manipulates the fundamental physics of thermal runaway mitigation. Every standard cell contains a pressure relief valve designed to aggressively vent superheated gases during catastrophic overheating events. Conventional battery designs point these exhaust valves upward toward the passenger compartment, mandating thick layers of heavy thermal shielding right beneath the cabin floor. This defensive barrier inherently increases both the vertical profile and the overall curb weight of the vehicle. By inverting the entire matrix, the pressure relief valves now aim directly downward toward the asphalt. The hazardous exhaust vector is entirely redirected away from the occupants. Redirecting the thermal venting trajectory downward allowed engineers to strip away dense internal shielding layers from the upper casing. The structural floor of the vehicle now absorbs defensive duties without requiring redundant materials stacked inside the energy module. This geometric inversion maximizes interior space. It aggressively drops the physical center of gravity. A lower center of gravity directly alters the dynamic roll axis for flatter cornering scenarios. Removing the upward-facing thermal barriers and integrating the cells into the skeletal frame compress the entire cross-section. The final consolidated profile of the integrated battery and floor system measures precisely 120 millimeters thick. This monolithic cell-to-body architecture generates the exact torsional rigidity required to harness over 1,500 horsepower. Dynamic lateral loads transfer directly into the battery block during tight apex maneuvers. The kinetic energy disperses outward through the unified metal skeleton, zero chassis flex. Engineers measure this structural resistance to twisting forces in Newton meters per degree. The technical data establishes a clear scale of rigidity. A heavy-duty Ford F-150 Raptor pickup truck peaks at approximately 25,000 Newton meters per degree. This electric sedan reaches 51,000, double the structural resistance of a specialized off-road vehicle. It even surpasses the carbon fiber tub of a Bugatti Chiron hypercar. That metric translates directly into track performance. When a vehicle hits a curve at high velocity, lateral forces attempt to warp the metal frame. If the chassis yields, the suspension alignment distorts. The structural battery deck eliminates this mechanical twisting. The driver experiences zero lateral roll. The car remains completely horizontal against the asphalt. With the main body locked in a rigid state, the shock absorbers execute their specific factory calibration. The tire contact patches maintain maximum surface area against the tarmac. The fundamental geometry of the foundation remains constant under extreme dynamic loads. The 51,000 Newton-meter foundation absorbs the immense rotational forces from 3 compact electric motors. These units deliver a combined 1,548 horsepower. Inside the casing, the rotors spin at 27,200 revolutions per minute. Standard high-performance electric motors hit a physical ceiling at roughly 20,000 revolutions. The difference is destructive. Pushing 35% faster generates massive centrifugal forces. A conventional stamped steel car would literally tear apart. The high-frequency vibrations would shear the standard structural joints over time. Such high rotational velocities demand a completely new material composition beforehand. Engineers lock the battery matrix, the customized alloy, and the high-speed motors into one continuous power loop. The synthesis of high-speed motors and a solid cast chassis immediately scales up on the actual assembly lines in Beijing. Traditional automotive plants rely on a century-old sequence. Stamping presses punch out hundreds of individual steel plates. Robotic arms spend hours fusing them together across a long factory floor. A standard car chassis demands thousands of separate spot welds just to maintain basic structural integrity. The conventional process is slow and complex. Xiaomi bypasses this entire timeline. The Beijing facility operates an enormous die casting press instead. The machine exerts thousands of tons of clamping force. Molten alloy flows into the steel mold under high pressure. The liquid metal fills every cavity within milliseconds before a water cooling system rapidly sets the final shape. One single operation produces a heavy monolithic rear underbody block. The entire printing cycle takes exactly 90 seconds. One monolithic casting permanently replaces hundreds of separate stamped steel components. The physical contrast on the assembly line is striking. Thousands of potential failure points along traditional weld lines simply vanish overnight. The resulting structural component is incredibly dense, completely lacking the hollow acoustic resonance of standard welded steel shells. This manufacturing shift supports high-performance metrics directly. The Xiaomi Vision GT concept car utilizes this exact structural philosophy. Engineers target exactly 1,900 horsepower for this specific vehicle design. That power output requires a chassis rigid enough to prevent the entire frame from twisting under heavy acceleration load. This is not a distant prototype projection. The large die casting machines actively shape metal today. The 90-second production loop runs continuously across multiple shifts. Every monolithic block exits the press completely ready for battery integration. The rigid structural floor directly absorbs the kinetic energy generated by the electric rotors. Older manufacturing templates suddenly look physically obsolete. The legacy era involved bolting an energy storage unit beneath a welded steel cage. The new method locks the power cells directly into the cast frame. Automotive engineers worldwide track these production metrics closely. Major global auto conglomerates now actively monitor the specific daily output rates of the Beijing factory lines. While legacy auto conglomerates study those Beijing factory metrics, other technology giants evaluate a much deeper market threat. The new manufacturing template operates effectively outside century-old industrial borders. How will established brands respond when consumer electronics manufacturers enter their sector? They must adapt quickly or simply copy this foreign assembly sequence. Corporations like Apple and Samsung now hold the capital and engineering foundation to build full vehicles from zero. A smartphone maker just rewrote fundamental automotive production logic in exactly 3 years.